All right, hi, eighth grade. So we're back starting a new investigation in our Thinking with Mathematical Models book. So if you have this, I'm going to be looking at the problem that's on page 31 if you want to follow along there, but you can also see it on your screen here. I'm going to mark it up on this so you guys can see the graph a little better. So we've been talking about whether a function is a linear function or not, remembering it has constant change. It looks like a line when you graph it. Then we figured out how to find the slope of a line. And we figured out how to write an equation of a line in slope-intercept form. So we're just kind of coming back to the beginning of that circle and talking about linear patterns again. So how can you make a line that models a real situation rather than just a bunch of points that don't have any context around them? So here it says, this is referencing that first thing we did when we were back in the building for that first week, where there was that experiment about how strong a bridge is depending on how many trusses there are, right? But this is an experiment that talks about how thick a bridge is and how many pennies it took. So a little model bridge, how many pennies it took for that bridge to break. So what this means in this table is that if the bridge was one thickness, had a layer, only one layer of thickness, it could hold 12 pennies before it broke. If it had two layers, it could hold 18 pennies. If it had three layers, it could hold 32 pennies before it broke. Four layers, 40 pennies before it broke. 5 layers, 48 pennies, and so on, right? So if I look at this, I'm trying to see, is it a linear function? Let's check. Well, to get from 12 to 18, that is plus 6, right? Plus 6. All right. To get from 18 to 32, well, that's plus, what is that? 28, 14, right? And then the next one is plus 8. So it does not meet the criteria of being a linear function right now because the amount it's changing each time is not the same. It's increasing, but by different amounts. So I'm going to erase that. Okay, so that doesn't mean, though, that we can't model it or use a linear function to predict things, right? It's because in real life, it's really hard to find something that's exactly linear. So what you do is you look at the graph to see, does it make a linear pattern? So this table here has been graphed over here, the points, right? One layer, there's 12, two layers, there's 18, all the way up to 6 layers. So the question is asking us, you can see that the points do not lie exactly on a line, but you can draw a line that is a good match for the data pattern. Drawing such a line gives you a model for the data, right? So let's see, what line would I draw for a model for this data pattern? So I might go, well, I know that if it's 0 layers thick, it can hold 0 pennies, right? So it might be here. And then I'm just going to be like, if I had a ruler, this would be much better, right? Is there a line thing on the side of this? No, so I'm just going to go at it as best I can, right? So you can just see if I had a ruler, I could probably do a better job of this, but I predict my line might be something like that, right? And that's just my estimate of the linear function. And how could I find an equation for that? Well, you guys know this. Let me change to a different color so you can see. So my equation is this. Sorry for my sloppy handwriting, right? We know y equals mx plus b. We know m is slope, b is y-intercept. Right here, I can see my y-intercept has come out to be 0 because when it's 0 layers thick, it can't hold any pennies. That makes sense. My slope, so if I'm going to estimate my slope, so this is me hand drawing it. So you can see it doesn't really cross any exactly. I know it crosses 0, 0. And then maybe somewhere I can estimate it's right here, right? So I could say my slope is whatever this triangle is. So that would be up 10, 20, 30, 40, 50, 60. So my slope would be 60. It's positive, it's going up, right? Over, what is this? My y is 1, 2, 3, 4, 5, 6. So my slope is about 10. And you can see that I estimated that because my dot over here is not exactly on the corner. I'm just estimating, which is what you're going to have to do when you're sketching a line that's not exact. So if I came up and plugged that in, I'd have y equals 10x plus 0, which is just the same as saying y equals 10x. Okay. So that would be my equation if I had to estimate by doing this thing by hand, my equation of the line. And remember, when I did the rise, I had to count by tens because that's what this axis is. And when I did the run, it's by ones. So I did 60 over 10, and it's about 10. That's my approximation. So let's see if we can get more exact. So I'm moving on to page 32. Excuse me. 32 has some graphs for us on problem A. It says the lines in figure 1 and figure 2 below represent two different equations or models for the data. So basically one person made this sketch, another person made this sketch, right? This one looks pretty close to mine, the second one. The line in figure 1 connects the points at the left end and the right end of the plots. So what this person did was they said, I'm just going to take this first dot here, make it blue so it's the same color. I'm going to find my first dot, then find my second dot, put my ruler so it touches both of those, and then just connect them. That's how they got that line. Then for this person, for figure 2, what they did was they said it passes among the points but hits none exactly. So they kind of did what I did and was like, I'm going to draw a line that kind of goes in the middle of the points. Some are above, some are below, right? So that's what this line did. Which of these two lines seems to fit the data better? Explain your choice. And can you sketch a line that is better fit than these two? Okay, so if I'm looking at these, which one do you think is a better choice? Which line models the data better? All right, and hopefully, so take a look a second and think. What do you think? Now I'm going to write a note to put an ed puzzle question here. Okay, so if I'm looking at this, how can we figure out which is better? Well, usually when you're trying to figure out which line is better, you want to look at where the points lie, right? So if we look at model 1, the line is close to the points, but if you look at this pink line is, besides being on these two endpoints, it's above all of the other ones. It's an overestimate for all of these points. There's a little bit of space between where the point actually is and the line is. So this one, I'm just going to write, is an overestimate. Maybe I can type and save myself some. Yes, okay. Now, thank you for dealing with me. So let's see if I can do this. This is an overestimate. Okay. And let's make this a different color so you know this is my text. And it's an overestimate, which I would write in my notebook because it falls above, the line falls above. Maybe I can type that here. The line falls above most of the points. Let's make that actually fit over here, right? The line falls above most of the points. Put that on the side. Okay, so you can use it to estimate, but you know you're going to be overestimating each time. All right, what about figure 2? So if I look at figure 2, this line is right here. We have 3 points that are above the line and 3 points that are below the line. So that is telling me figure 2, all right, half of the points are over the line and half are below the line. So because this one is an overestimate for some and an underestimate for other, this, I would say, is the better fit, right? Because sometimes we're overestimating, sometimes we're underestimating. So on average, we're about the same. They cancel each other out, right? And so could you draw a better fit? Yes, if I could print this out and actually, I don't know, I think figure 2 is pretty good, but maybe you could get a line that's more exact, remember? So one of the keys to drawing a line is to make sure, and I'm going to just do this in a different color over here on the side. So when you're drawing your best fit line. You are trying to draw a line in the middle of the points. The same amount below and above, right? So you're trying to draw a line that when it splits the points down the middle, half of them are above the line and half are below. So get that in your notebook, right? Pause it if you need more time. We're going to do some more examples. All right, I'm going to scroll down. B says, so there's a mathematical way to find out how accurate your line is. You calculate this thing called the residual. The residual just tells you how far above or below the line you are. So if I come over here, I write the residual tells you how far below or above the line a point is. I'm going to go over that. If you find the residual, it literally tells you the distance from the line. So if I went up here, the residual would be the distance from this pink line to the blue point. So how far away that is, right? It was this distance below. So we're going to actually go ahead and do that. So this says, if I look at figure 1 and 2. So they want us to do it twice for figure 1 and for figure 2. So we're just going to do it for figure 1 right now. Okay, and then I'll erase it and do it for figure 2. So for figure 1, these are the number of layers and the actual number of points from that table on that first page. So what did the line predict? So let's go ahead and do this. So the line predicted, let me get a color ready. So if I go at 1, the line predicted that it would be exactly 12. That's where it falls, right? Because that person just drew a line through the first point and the end point connected them. Okay. Now, if I use the line at 2, what did the line predict how many pennies it would hold? Well, at 2, the line predicted that the number of pennies would be right here. Okay, that's above this blue line. What number is it about? I'm going to say it's about 22. Okay, 22, 23, somewhere in there. It doesn't matter. 22. Okay, at 3, the line predicts pretty close to where it's at, right? It's like right here. So it was 32. It's a little bit higher. I'd say 33. That's 33. Okay. When there's 4 layers, the line predicts that it would hold this many pennies, which is about, if I come over here, it's about, I would say 43. I'm just estimating. If your answers are off by 1, it's not a big deal, right? Because we're estimating. All right, if the bridge is 5 layers thick, my line is predicting it's right here, which is about right here. I'll say 53. And then last but not least, 6 layers, my line was right on the dot because I used that to draw the line, and that was at 64. Okay, so that part now helps us find the residual. All you do for the residual is take the actual number and subtract the bottom number. So for example, I'll do number 1 right here. So for number 1, I would do 12 minus 12. Well, that's 0. I'm not going to write that down. For the second one, it's going to be 18 minus 22. Okay, so what's 18 minus 22? That's a negative number, right? It's negative 4. So I'm going to come in my chart and write negative 4. And why is it negative? So let's look at number 2. It's negative because I predicted with my line it would be up here, but it was actually below. So the negative 4 means my line or my point is below by 4, right? So this negative is actually telling me I made an overestimate of 4. Kind of the opposite of what you think. So I'm going to write overestimate. I should have typed again, but thanks for bearing with me. Okay. Now let's do the next one. 3, for point 3, it's 32 minus 33. 32 minus 33 is another negative number. Hopefully you guys are remembering that it's negative 1, right? Negative 1. So negative 1 goes in here. All right. 40 minus 43 is the next one. 40 take away 43 is negative 3. Use your calculator if you're wanting to check me. 48 minus 53. 48 minus 53 is minus 5. And 64 minus 64 is 0. Okay, so if I look at this, this agrees with what I said up here. Remember I said in this red part that figure 1 is an overestimate because the line falls above most of the points right here? My table is proving that to me, right? All of these numbers are negative, which means it's an overestimate. And it's an overestimate of a pretty big number, because if I added all these, I would get -4 plus -1 is -5. -5 plus -3 is -8. And -8 plus -5 is 13, -13. So I overestimated a total of -13. Okay, so that's kind of how I can see that it's a big, there's a big difference here between my line and the points. So now if I erase, so copy that down, because I'm going to redo this for figure 2. Okay, so let's redo this for figure 2. I don't have another chart, but you guys can draw another one real quick. All right, so for figure 2, let's see if it's better. Okay, and I'm just going to remember, I'm going to make a different color so you guys know I'm talking about the different one, right? Let's do purple. So this one's for figure 2. Okay, and I'm going to remember that figure 1, I'm just going to write over here, was minus 13 altogether. Okay, so figure 2, we have to do the same thing. Let's come and look. Actual was 12. Predicted by the model is slightly below. I would say it's like right on 10. So I'm going to put a 10 there. At 2, the line predicts it's right here, slightly above. I'm going to just say it's 20. At 3, oh, this is looking nice and easy. At 3, it's slightly below at 30. At 4, it's a little bit above, or exactly actually, it maybe is like 41. Is it 41? Yeah, I'll put 41. It's a little bit above 40, right? At 5, it's above this one. I'll say it's at 51. Remember, we're just estimating. And then at 6, it's a little bit below. It's right here. It's a little bit above 60. I'm going to say 61. All right, so now let's find the difference. 12 minus 10 is 2. 18 minus 20, that's a -2. 32 minus 30, that's 2. 40 minus 41 is 1. 48 minus 51 is -3. Again, I'm not explaining these, but you can use a calculator to check. And 64 minus 61 is 3. All right, hopefully you're noticing what's different from the last figure is now these aren't all negative. Some are positive and some are negative. Why? Because some parts the blue dots below the line and some parts the blue dots above the line. So now let's add all these up. 2 plus -2, well, that's 0. 0 plus 2 is 2. 0 and 2 plus 1 is 3. 3 plus -3 is 0. And 0 plus 3 is 3. So when you add all these up, it comes up to 3. And when you added all of them for figure 1, it's -13. So just by looking at those, which number is absolutely smaller, right? So which one's closer to 0 is what we care about. And you guys should be able to tell that 3 is much closer to 0 than -13. That's why this is a better estimate. So there's 2 ways you can prove a line is a better fit for a model. One is that when it's drawn, half of the lines are above and about half of the points are above the line and about half of the points are below the line. That's one way you can check. How does it look? The second thing you can do is find all your residuals for your set of points, add those up, and whichever one is the number that's closest to 0 tells you that it's a better fit. So in our case, figure 2 is better because 3 is much closer to 0 than -13. All right, we'll keep working on this. I know that was a lot for this one lesson. And I'll see you guys next time. Also, if you saw me look into the door for a second, it's because my son is trying to show me his drawing. So I'm going to go take a peek at it. And if you want to know what it was, ask me after this video and I'll tell you. Okay, see you guys.